Okay, next question. I've got another quadratic equation here, and I want to do the same thing as last time. I want to sketch the parabola and show the intercepts, turning point, domain range, axis of symmetry, all the same stuff. Now, the question that I've chosen here does not factorize nicely into uh, whole integers in its factorized form. So if we say this is equal to y, how do I find my uh, x-intercepts if I can't factorize it nicely? Now, I could still factorize it via completing the square, and that gets me into the turning point form first, and then using the a plus b, a minus b method, I can get it into its factorized form. But that's going to get quite messy. I'm working with a whole bunch of fractions each time I do that. Um, but it is possible. Now, instead of doing that though, if we can find a general equation such that we can just find these points based off of that equation, it's going to be much easier than doing that whole completing the square, then putting it into its factorized form afterwards. So let's look at how we would do that. So I've pre-written this out just to make it go a little bit faster. Now you don't have to follow all of this, but it's hopefully you'll be able to keep track with it though, because we're still following the same techniques that we've already gone over. Now, if I have a very generic equation, ax squared plus bx plus c, and I'm letting that equal to zero because I'm trying to find those x-intercepts. In this particular case, we're doing it for any a value, except when a is equal to zero. Because when a is equal to zero, you don't have a quadratic, you've got a linear equation. Now, the way we're going to do this is we're going to complete the square, same as what I just said. It's possible to get into this factorized form via completing the square. So we're going to do the same approach, except on generic letters that represent the equation. So I'm going to first divide everything by a because when I complete the square, I still want a 1 in front of that x squared component. And then I see what I'm going to get in terms of the square. So if I have an x plus, I want to end up with a b on a. So let's say x plus half b on a times by x plus half b on a. I end up with an x squared component, a half b on a x. So I have two of those, and I end up with a half b on a all squared. Combining that, I have x squared plus a full b on a x plus half b on a squared. Now, when I'm completing the square, I want to look for my b on 2 value, my b on 2 squared value. Um, my b value in this case is b on a. My b on 2 will be b on 2a, and my b on 2 all squared will be b on 2a squared. So same process as last time. I'm adding and subtracting this b on 2 squared term first. So I'm adding and subtracting b on 2a squared. And then the first three parts completely factorize or become a complete square as x plus b on 2, where our b on 2 is now b on 2a. The remaining stuff can be combined by finding a common denominator and simplifying that. So these are still equal to zero on this side of the equation because we're trying to find where y is equal to zero. Now, to scale this to a common denominator, we could cross multiply, or we could just scale this one to have a denominator of 4a squared. So if we were to times both the numerator and denominator by 4a, that'll get us there. And I'm now at this point here. So I've scaled this one to have the common denominator. And we can now put all of this over the same denominator. So you'll have a negative b squared and a positive 4ac. So we can move this over to the other side of the equation. So the b squared becomes positive, the 4ac part becomes negative, and we are left with this. They're still trying to find what that x value is or what those x values are. So making x a subject of the equation, I next have to square root both sides. Now, whenever you're square rooting something, you have to be careful whether it's going to be a positive or a negative as the previous thing. And so if we have -2 squared, for instance, or +2 squared, both of those will give us a +4 value. So square rooting 4, well, it could have either been a positive or a -2. So when you square root both sides here, you're going to end up with a plus minus out the front of this square root symbol now. And the square root of a squared term, the square disappears. So you've just got x plus b on 2a left on this left-hand side. Now, you can see that you have 2a as a common denominator for everything that's not the x component. So we can collect our like terms, bring this b on 2a over to this other side. So it was initially a positive b on 2a, so taking it over to the other side becomes a negative b on 2a, and you just bring it all under the common denominator. So all over 2a, so negative b plus minus this square root chunk of stuff. So this formula is actually the quadratic formula, something that you'll hopefully seen in class already. And you can see it was derived for a not equal to 0, and it was derived for y equal to 0. So we're trying to find those x-intercepts. So where the parabola crosses that x-axis. And A, B, and C in this equation directly link to your coefficients of your quadratic equation. Now, one other thing worth noting before we actually dive into the question is because you have a chunk of stuff plus minus another chunk of stuff, this square root symbol is called the discriminant. And so this tells you how many intercepts your graph is going to have with that x-axis. For instance, if this is equal to 0, there is not going to be any plus minus stuff. And so you're just going to have one intercept. And that's going to be when the turning point hits the x-axis. And so the turning point also tells us our axis of symmetry location. So this negative b on 2a is your axis of symmetry. And this discriminant tells you whether or not you have 0, 1, or 2 x-intercepts. So number of intercepts, well, when that's equal to 0, you have one intercept. When b squared minus 4ac is positive, so greater than 0, you're going to have a number here, and therefore you're going to have b plus that number and negative b minus that number. So you're going to have two solutions. Therefore, you're going to have two intercepts on your x-axis. And then you've also got another case where you have b squared minus 4ac ends up being a negative number. So a negative within a square root means that you're going to have an imaginary number, so no real solutions. So we have 0 intercepts, real intercepts. And that might be the case when you have a quadratic that is offset from the x-axis. Okay, going back to the equation. Now our a value is 1, our b value is -11 on 10, and our c value is -3 on 5. And we want to plug those values into our quadratic formula to find those x-intercepts. So negative b, so negative negative, so we have positive 11 on 10 plus minus square root b squared, so 121 on 100 minus 4ac, so 4 times by a value times by c, which is -3 on 5, all over 2 times by 1. Simplifying this, we have x equal to 11 on 10 plus minus square root. Now we're going to have 121 on 100. So we want to get this to the common denominator of 100. So first we figure out what it is. So that's negative negative is going to be positive. So we have 12 on 5 plus 12 on 5. And to get that to 100, I'm going to scale it by 20 on 20. all over 2. So x is equal to 11 on 10 plus minus square root 121 plus 240 on 100 all over 2. X is equal to 11 on 10 plus minus 361 on 10. So pulling 100 outside of the square root all over 2. In this case, it just so happens that square root of 361 is perfect square, so it pulls out as 19 all over 2. Okay, so when you've got something like this, so you've got a fraction divided by a number, if we just look at this on the side here, so let's say you have 11 on 10, and we're just looking at this first part, we're dividing that by 2. You're using your keep, change, flip technique. So you're keeping your 11 on 10, you're flipping your sign from divide to a times, and it becomes 1 on 2. So the denominators multiply, and we end up with 11 on 20. So what you can see is when you have something like this 10 is at the same level as the 2. So x is equal to 11 plus minus 19, all on 20. So that 2 is brought together with both of those 10s because they had a common denominator. So we have two valid solutions. They're going to be 11 minus 19 and 11 plus 19. We have 30 on 20, and we have negative 8 on 20. Simplifying these, first one becomes 3 on 2, and the second one becomes, well, these are both even, so it'll be 4 on 10, again, both even, so 2 on 5. The negative out the front. Now, this was a tech-free way of doing this, but you could have also plugged this quadratic equation into your calculator. So you could have plugged the coefficients into this formula and then done msolve, gsolve, whatever it is you have on your particular graphics calculator. So what we've done so far is we've found the x values for those x-intercepts. So we have, with the starting equation, we have negative 2 on 5, and we have positive 3 on 2. Now we can find our y value, y-intercept, when x is equal to 0. And so you're left with just your c value, so negative 3 on 5. That means the turning point's down here somewhere as well, which makes sense because the graph is going to have this structure because you have a positive a value, so everything still looks right. Next, we want to find our turning point. So instead of putting this into the turning point formula, because we already have our axis of symmetry based off of this quadratic formula, where our axis of symmetry is negative 11 on 10 divided by 2. So everything excluding that plus minus, because that's going to be the center point. And we saw that 11 on 10 divided by 2 was 11 on 20. So our x coordinate for the turning point is 11 on 20 because it was negative b on 2a, and our b value in this case was already negative. So our turning point is positive 11 on 20. Now we're plugging in 11 on 20 into this starting equation. So 11 on 20 squared minus 11 on 10 times by 11 on 20 minus 3 on 5. And we're just trying to find what that y value is that goes along with that x coordinate. So we're plugging in a very particular x value into the quadratic equation. Now, 11 squared is 121 on 20 squared, so 2 times 2 is 400, and then you got one zero, so 20 times 20 will have two zeros, so 400 minus, again, 121 on 1 times 2 is 2, two zeros, minus 3 on 5. Now, you'd scale all this up to get a common denominator and simplify it, but for simplicity, I'm just going to plug these values into my calculator. So 121 divided by 400 minus 121 divided by 200 minus 3 divided by 5. And I'm getting this decimal here. So what I do is I hit this S to D button, and that'll take it back into a fraction if I needed this as a fraction. You can also see that this fraction was scaled to a common denominator of 400, which is what I would have done if I was to do this manually as well. So minus 361 over 400 is my y coordinate value for the x value of 11 on 20. And that'll be my turning point. So my turning point coordinates are 11 on 20, comma, negative 361 on 400. Or in decimal form, 11 on 20, it's a little bit over 0.5. And for this one, we had negative 0.9 effectively. What is 11 divided by 20? So exactly, it'll be 0.55. Okay, I've plugged this equation into Desmos. Now, if we look at the components that we've already found, we saw that we had x-intercepts at negative 2 on 5, so negative 0.4, and 3 on 2, so positive 1.5. We also found the turning point to be 0.55 and negative 0.9, and we found the y-intercept to be negative 3 on 5, which is negative 0.6. So that's what we've found so far. And instead of me just drawing it out and being quite messy, I've put this into Desmos. So let's finish this off. Let's find the axis of symmetry and the domain and range. So I've already made the point a few times now that the axis of symmetry is your turning point location for the x. So our axis of symmetry is x is equal to 0.55. X is equal to 0.55. That there is our axis of symmetry. Because you can see on either side of that blue line, it is symmetrical. Now, if we were to state our domain and range, you can see if I keep scrolling out, it keeps increasing vertically and it keeps increasing horizontally. Now, it's increasing vertically faster than it is horizontally, and so I'm not getting that the nice expansion horizontally. But if I was to keep scrolling out, the numbers would keep getting bigger and bigger, and I would eventually be going from negative infinity in the domain to positive infinity in the domain. So for the domain, I'm going negative infinity, positive infinity, which is equal to all real numbers. Now for my y-axis, so my range, it's going down to the turning point value, negative 361 on 400. And as you saw when I scrolled up, it kept going up in the graph. So it goes all the way up to positive infinity, but can't actually touch that value. So we have parentheses instead of square brackets. And that would be the domain and range for that question.